Okay, so some references I wrote down. I'll probably add some more as I remember them. But this is sort of the encyclopedic book, Conway and Sloan, Sphere Packings, Lattices, and Groups, also called SPLAG, S-P-L-A-G. It's not really a book that you can, I mean, it's not a textbook. It's more like a reference book, but it has a lot of, it's got a wealth of material and quite a lot of stuff about, the Leech lattice and codes and so on and so forth. So it's quite an amazing book. This Zong's book is more compact, but it has some typos, so just be aware of that. It has occasional mistakes. Martinet's book is quite nice, Perfect Lattices in Euclidean Space, so more focus on quadratic forms and low dimensions and things like that. Castles is a book on rational quadratic forms, and this is good for sort of the number theoretic side of things, but also has some decent descriptions of sort of Euclidean lattices. And it's quite, I mean, it also talks about indefinite forms and so on, genus, spinor genera, and so on. So it's a nice book for graduate students who are thinking about, learning about quadratic forms. Rogers has a classic sort of packing and covering book where he describes some of the older theorems. There's a book by Boratsky on finite packing and covering. And I think it has more focus on low dimensions like plane or 3 dimensions. There are some papers. So there's some of the bounds that I'll describe come from Cohn-Elke's new upper bounds on sphere packings. Then we use some of that in our solution of the Leech lattice. The fact that it's the densest lattice in 24 dimensions. So that's a paper that's 2009 or so. There's more papers I'll write eventually by other people and by us. And there's I don't remember the expository, the name of title of this paper, but there's a very nice expository paper by Elkes on which talks about lattices and codes and things like that. You can probably search for Elkes and notices of the AMS, and it should be freely available now. Okay, all right. So this lecture I want to talk about upper bounds for sphere packings, and there's quite a lot of stuff. So let's see how far we get. Okay. All right, so we'll go over a few different upper bounds for density of the densest sphere packing. We'll go over, so there's a nice compact theorem of Blichfeld. Then I'll talk a little bit about linear programming bounds, and I will assume some things that will get covered in I think lecture 5 or 6 on harmonic analysis. Are you the next one? Are you Monday morning, the first one? Okay. So it will get covered by Naru in the next lecture. So LP bounds, I mean, where these come from and where they're used. So mostly I'll be talking about asymptotic bounds, but I'll also talk a little bit about the specific sort of sharp bounds that you get in 8 and 24 dimensions using linear programming bounds. So let me just say Kabacanski. Lenventein. And I'll say they're bounds for spherical codes, and they're also the bounds for sphere packings, which are actually connected. They deduce a bound for spherical codes from linear programming bounds, and then they apply it to get a bound for sphere packings. So we'll see how that works. And then I'll talk about the Cohn-Elkes bound, and probably its application to 8 and 24 dimensions. Okay, so let's start with sort of a nice clever proof. So Blichfeld's theorem says the packing density delta of Sn in n dimensions is bounded above by n plus 1 over 2 times 2 to the minus 0.5 n. Okay, so the exponential rate of growth is minus 0.5 in this case. Okay, and it'll get improved by other asymptotic bounds. But let me make a comment about notation also with respect to Radhika's lecture. So this is from Zong. This sort of notation is from Zong. So Sn, Zong sort of abuses notation a little bit. I think he uses Sn. So Sn you should really think of as the n ball. So it's really what I called Bn in the first lecture. And so I just want to make a point of, so Sn, so just think of this as delta of Bn, okay, wherever you sort of, and on the other hand, I've used this notation Sn minus 1. This is really the sphere in n dimensions of dimension n minus 1. Because that's distinct from, so that Sn minus 1 is distinct from this Sn, the boundary of, anyway, hopefully everybody understands what we're saying. But also, delta is different from delta star. So I think Radhika used delta star. Star was referred to restricting to lattices. So when you would only look at lattices and look at their density, you would put a star and say delta star of Sn. If you look at all sphere packings, then you would say delta of Sn. Okay. So all right. So this proof is quite nice and elegant and relatively straightforward. So I'm going to do it in detail, and I'm going to follow Zong. So okay. So the main idea is the following. Of his proof is the following. So suppose that let C be the centers of the packing in Rn, right, of unit balls, so that C plus Bn as a set sum. This is the area that's covered by the packings. Okay, so area is the volume, sort of, is the region covered by the balls. Okay. So his idea is the following: let R be some radius that's bigger than 1, R bigger than 1, and you replace this packing x, for each x in C, replace x plus Bn, the n ball, by the scaled ball scaled up to radius r, x plus rbn for x and C. But what we're going to do is we're going to fill this region. So fill each of these balls these being the new ones with a variable density. Right, so normally we assume that the balls have density 1, and so then you count how much density is it, how much volume is covered within them, as opposed to all of space. So we're going to fill them with some material of variable density, such that the total mass or total density at any point of Rn doesn't exceed 1, at most 1. Okay. So if you do that, then the total mass of this collection, x plus Bn, x and C, intersect, let's say, so look at all the radii that are inside the cube of this size, L minus R. So In is, I should say In is minus 1, 1 to the n. So you scale it up by L minus R. So if all the centers are, have all coordinates bounded in absolute value by L minus R, then the whole ball is contained in the cube LIN. Okay, that's the point. Okay, so yeah, so the total density, I mean, this just means the total density, right? So you're filling each of the balls. Now, you've scaled up the balls by radius r. So each of them is going to contribute some density. Each ball is going to contribute some density at x. Compute, yeah, but they may overlap. So you sum all the densities and should not exceed 1. Right? So the point is that if you now look over all space, each point has total density less than or equal to 1. So whatever when you sum up over all the balls, that can't exceed the volume of space. I mean, right? Sorry? L minus R. So yeah, L is some large number, so it doesn't, yeah, I'll just say it doesn't exceed sort of the volume of LIN for sort of L some large number. L some large positive number. Okay, so think of a large cube, and you take only the centers which are sort of, interior enough so that the balls around them of radius r don't go beyond the cube of size L. Yeah, L is going to be some large number that we're going to choose. The variable density is chosen first. Yeah. L is going to be something that we use in the analysis at the end, right? I mean, this is going to be something we take a limit as L goes to infinity. Good question. Mass is just the total. Yeah, I mean, so it's just the total density because the balls are going to overlap. So each ball is going to contribute some density at x, and you take all the balls that contain x, and you sum up all the densities. That's the total mass. I mean, this the total density does not exceed 1. Okay, so is this clear? So the basic idea is clear, and then we're going to use this fact to bound the density of the original sphere packing. Okay, so all right, so let's get started. So I'll describe what this this the main the goal is to choose an R and to construct this variable density. Okay, so how do we get there? So lemma 1, let x question. Sorry? Oh, exceed the volume. Okay. Volume. Larger? Okay. Let x1 dot xm be r to the n vectors. So then the sum of jk going from 1 to m of xj minus xk norm squared is less than or equal to 2m times the sum of j going from 1 to m of x minus xj squared. Oh yeah, x is also some vector. X, x1, x through xm are in r to the n. Okay, so that's the first lemma. So all right, let's see why this is true. So proof. If you have real numbers, so if a1 through am are real numbers, then the total mass of, oh yeah, that's a good question. RBN, you're right. This should be, sorry. Thanks. The total mass of that doesn't exceed. So then what? So then if you take the sum of aj minus ak squared jk going from 1 to m, let's compute this. So this is sum of aj squared plus ak squared minus 2aj ak. And this is sum of aj squared plus ak squared minus, so this sum minus twice the sum of aj, j going from 1 to m squared. Okay, this is just a, I'm taking all these products and just putting them into, rewriting that double sum. Okay, so and then therefore this is less than equal to whatever this number is, it's non-negative. So you're subtracting a non-negative number, so this is less than equal to whatever this sum is, which is twice the sum of aj squared. Okay, so this is for real numbers, and then if you want to go to vectors, so then you let yj be x minus xj, then sum from j going from 1 to, so jk going from 1 to m of yj minus yk squared, that's equal to sum of, so yj was just x minus xj, so yj minus yk is just xk minus xj, so this is the same as the sum of xj minus xk squared, and then that's equal to sum, I'm just going to sum over the coordinates so we can reduce to the real number case, I going from 1 to n, some jk going from 1 to n of y sub ji, sorry, x sub yeah, x sub, what did I want here? Yeah, x sub I guess I want the other way, yeah. I mean, this equals this, and then from here I'm going to go, I'm going to say yj, that this equals yji minus yki squared, and then that's equal to, right, that's less than equal to twice m sum I going from 1 to n of sum of y ij yji squared. I do this right? Yeah, so that part follows from the lemma, and so then that's equal to twice m sum I going from 1 to m of the norm of the vector y sub I squared, which is equal to twice m sum j going from 1 to n of x minus xj squared. Okay, so all right, so that proves that lemma. Then is that clear? So lemma 2 so let n be positive and sigma from r greater than or equal to 0 to r be such that, so there's some function such that sigma of x is non-negative and it's 0 beyond r, and so it's non-negative and continuous, and for 0 less than or equal to x less than or equal to r, and sigma of x equals is identically 0 for x bigger than, sorry, a little bigger. Okay, yeah. Is this legible? This is okay. Okay, all right, I'll increase the size. All right, so then suppose for each packing Bn plus C, that the following holds, that the sum over xi in C of sigma of x minus xi is less than or equal to 1, holds for all x and r to the n. Suppose that holds. Suppose this function defined such that for all packings this is true, then the density of sphere packings is bounded above by J inverse, where J is n times the integral from x from 0 to r, x going from 0 to r, of x to the n minus 1 sigma of x dx. Okay, it's just some total mass of sigma. Okay, so all right, so why is this true? So proof. So let L be a large number, and suppose there exist m spheres Bn plus x1 dot 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 Bn plus xm that are contained in, that are fully contained in Lin. Okay, that big cube from minus L to L to the n, right? So then xi plus r times Bn, if you scale up the ball, that's going to be contained in L plus r in. Okay, and because all the centers of the cubes are contained in Lin, and so you can go at most r beyond, right? So for yeah, sorry. So what? So so we compute V, the volume of L plus R in, right, bigger. That's at least the integral of over L plus R in of sum going from 1 to m of sigma of x minus xi dx. I mean, the point is that this sum is bounded by 1 by hypothesis. Right? We are assuming that for any packing, the sum over all points of the packing of x minus sigma of x minus xi is at most 1. So whatever the sum is at most 1. So this volume is at least this integral, and you switch, right? So then you can write this as sum of I going from 1 to m of integral r to the n sigma of x minus xi dx. So now I can freely roam around all of r to the n rather than just this box, because once you're outside of that box, you know that sigma has to vanish there, right? By the other hypothesis. So namely, here sigma of x equals 0 for x bigger than r. So if x is outside of that ball, then sigma of x minus xi is going to be this distance is going to be at least is going to be bigger than r. So sigma is going to vanish there. Okay, so let me just say this implies this. Okay, and so then this is so now this is equal to m times all these. Since you're allowed to roam around Rn over all of Rn, you can translate this integral, and so this is just m times the integral of sigma of x dx over r to the n. And well, then you just sort of write down the volume element. Since it's really an n-dimensional integral, this is equal to m times the integral from 0 to r. I'm going to convert it to a radial integral. So sigma of x d of this is the d of this thing. This is the volume of the n ball, and so this is the surface area element. Okay, so this equals this, just converting to the radial integral, and this is m times n times omega n. Just take the differential times the integral of from 0 to r of x to the n minus 1 sigma of x dx, which is m times omega n times j. Okay, the way I've defined j had the factor of n in it. All right. So density, which is the supremum over all C of lim sup over L goes to infinity of m omega n. So, right, inside I mean, the way, I mean, you take all the balls that are contained inside that cube. There's m of them, and so that's the volume that they cover. You can ignore the stuff at the boundary. It's not going to matter in the limit. And this is less than equal to lim sup as L goes to infinity of volume of L plus R in over J volume of in, and this volume and this volume, well, in the limit there, this should be LIN. Those volumes, the ratio is 1 in the limit, so J inverse. Okay. Right. Any questions about this lemma? Okay, so once we come up with this function sigma, then this J inverse gives us a bound. Okay, so the question, how do we come up with this variable mass density? So need to come up with this. Need to come up with a suitable sigma, and that's what the first two lemmas are going to get us. The first lemma, I guess, is going to get us. So let C plus Bn be a packing, and enumerate sort of the points of C as x sub I1, sorry. Hold on a second. Sorry, x1, x2, etc. Okay, just enumerate the points of C somehow. So then we have xj minus xk, since it's a packing, that length is at least 2 for j not equals k. So by lemma 1, you have the following inequality: sum from jk going from 1 to m, x sub ij minus x sub ik squared is at least 4m m minus 1 for every finite set of distinct indices I1 I sub m. Okay, right? So every pair of distances is at least 2, so the square gives you 4, and there's m times m minus 1 choices. Okay, so for every x in R to the n, we have some, I guess I haven't used lemma 1 really so far. I'm going to use lemma 1 now. Okay, so sum from j equals 1 to m of x minus x sub ij squared, I sub j squared, that this is at least, so remember there was a factor of 2m, so this is at least twice m minus 1. Okay, that's what lemma 1 gives you. For any x in R to the n, that's true. All right. So then you define sigma of x equals the maximum of 0 and 1 minus 1/2 x squared. So this function is continuous up to, right, I mean, what does this function look like? So it starts at 1, and then at r equals the square root of 2, it becomes 0, and then you keep it at 0. So okay. So for every point x in r to the n, we have the following. So we have sum of, if you compute the sum from I going from 1 to infinity of, so over all the points of the packing of x minus sigma of x minus xi. So first of all, you only look at things which are within radius square root of, within radius r, which is square root of 2. So this is equal to sum from I going from 1 to m of sigma of x minus x sub ij, j going from 1 to n, where this is the subsequence of indices for which those points are within square root of 2. So where I1 dot 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 IM are the indices such that x minus x sub ij is less than or equal to square root of 2. So that's the first thing. And then this is, what is this equal to? So this is equal to sum from j going from 1 to m of 1 minus 1/2 x minus x sub ij squared, right? And by definition, and then this is equal to m minus 1/2 the sum of x minus x sub ij squared, j going from 1 to m. And so this is equal to m minus, this is less than equal to m minus 1. Right, so 1/2 of twice m minus 1, so this is equal to 1. So you get that the property that we want of sigma holds. So sigma of x satisfies the conditions of lemma 2. And you can compute what j is the integral, n times the integral from 0 to square root of 2 of x to the n minus 1, 1 minus 1/2 x squared dx. This is easy. It's 2 over n plus 2 times 2 to the square root of 2 to the n, or 2 to the 0.5n. So density is bounded by j inverse, which is n plus 2 over 2 times 2 to the minus 0.5n. That's the end of the proof. Okay. Yeah. So this is not. So people have made improvements upon this proof, and I think, let's see, what is the best exponent that. Yeah. So let me just write down a remark. So this was improved by Rankin, Sidelnikov, Levenstein, etc., and they get better asymptotics as well. So improved by Rankin. So you can get density bounded by 2 to the minus 0.5523 n 1 plus small o of 1. You can make improvements upon this. So yeah, I believe right. I mean, I think the idea is the same, to choose different mass, but choose different sigma. Yeah, I'm not sure of. I haven't actually read these papers, but I assume that's the improvement they have, choosing different sigmas. Questions? Okay, so let me say that the mean minimizes the quadratic deviation. Well, I mean, it gives you a bound on the deviation, right? Let me just see. Yeah, that's correct. I mean, equality holds exactly when it, yeah. I mean, when you have the mean. That's correct. You could, yeah, I assume you could, yeah, you could use, yeah, not just the square. You could try to use something else. That's correct. Yeah, you could use a fourth power or something like that. Yeah, I'm not sure what people actually use, but I mean, you could. It doesn't have to be a power. It could be some function, some different function. Yeah, good point. Okay, so let me say a few words about linear programming bounds. I'm not going to do the whole setup, but some key facts I want to state, and then I'm going to roughly outline the asymptotic bounds that you get, which Kabacanski and Lenventein wrote down, and then we'll see. I mean, I may, depending on how much time I have, I may either go over a little bit or continue on Monday afternoon. We'll see how it goes. Section 2. So LP bounds and Kabacanski, Lenventein. Okay, so so LP bounds were introduced by Delsarts. So LP bounds are linear programming bounds. Linear programming bounds. So these were introduced by Delsarts. And in the setting of things like binary error correcting codes, association schemes, this is combinatorial setting. So for association schemes, binary codes, spherical codes, etc. And they follow from they follow from properties of what are called positive definite kernels. Positive definite kernels, or PDKs, which are certain functions on appropriate spaces which satisfy certain positivity properties. So we'll describe them. But they're extremely useful in all sorts of upper bounds, linear programming, semi-definite programming, and so on. So we will spend a little bit of time on these things. So I'll briefly introduce them, and then they'll be discussed more in the next lecture. And they were used to give asymptotic bounds first for spherical codes by Kabacanski, Lenventein, and then I'll say how that's used to get bounds on sphere packings as well. Okay, so let's say something about positive definite kernels. Okay, so So I'm going to restrict to the setting where we have to the sort of spherical setting, just because it's sort of simpler. But there are many other settings in which you can define positive definite kernels. So f on the interval from -1 to 1 is a real valued function, is called positive definite. It's a positive definite kernel if so on, and this is on Sn minus 1. So the relation between Sn minus 1 and -1 to 1 is that if you have two vectors on the unit sphere, their inner product is between -1 and 1. So this is sort of the set of inner products. So it's going to be a function that's defined on the set of inner products between points, and it's going to, you say it's a positive definite kernel if for every spherical code C in which is x1 dot 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 x capital N in Sn minus 1, we have the following property. The matrix F evaluated all the inner products xi, xj. So this is going to be a capital N by capital N matrix indexed by I and j, and the ijth entry is going to be this thing. F evaluated there, I comma j, is positive semi-definite. Okay, so then you say such a function f is a positive definite kernel. So for instance, if f is the constant function 1, that's a positive semi-definite. So this matrix is the all ones matrix. That's clearly positive semi-definite. So that's a trivial example of a positive definite kernel. But there are many non-trivial positive definite kernels. And in fact, one of the key things is that there's a classification of these things. So there's a theorem. Theorem of Schanberg, which classifies positive definite kernels for Sn minus 1, which says that, so basically what happens is there is a sequence of one variable polynomials, one for each degree, and a function is positive definite if and only if it's a positive or non-negative linear combination of those specific polynomials. Okay, so there's a sequence of, these are called ultraspherical, they have many names, ultraspherical or Gegenbaner polys. For now, let me just call them G sub n I. N is the dimension of the space. I is an index going from 0 to infinity. I goes 1 dot dot dot. Okay, and n is the dimension of the space, such that PDKs are exactly the positive cone spanned by these. Okay, so something is positive definite if and only if it's a non-negative linear combination of these Gegenbaner polynomials. And you can write them explicitly. There's a second order recurrence for them. I'll mention some properties of these things very soon. So before I do that, let me just note one thing. If the matrix is positive definite, in particular, multiplying on the left and right by the all ones vector, we see that for any positive definite kernel f and any spherical code, the sum of f of xi, xj is non-negative. Okay, for any PDK F and spherical code C equals x1 xn. Okay, that property we'll use shortly. Okay, so right. So let me write down a few properties about these polynomials, these Gegenbaner polynomials. So say some words. So Jacobi. So there are special cases of Jacobi polynomials, which are again special functions. Okay, so Jacobi polynomials. Polys are a family of special functions indexed by two indices alpha and beta, so p sub p alpha beta, and also by a variable, an index k, which goes from 0 to infinity, 0, 1, dot, 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 infinity, such, so this k is also the degree of this polynomial. So p alpha beta kt equals, here's an explicit formula for them, 1 over 2 to the k, sum of I going from 0 to k of k plus alpha, choose I, k plus beta, choose k minus I, times I plus 1, sorry, t plus 1 to the power I, and then t minus 1 to the power k minus I. Okay, so anyway, you can see that the degree is bounded by k, and it's exactly k. Okay, and here alpha is bigger than minus 1. Alpha and beta are real numbers. Alpha bigger than minus 1, beta bigger than minus 1, parameters. And the Gegenbauers, let me leave the references actually, leave them up. So if you set alpha equals beta and set them equal to n minus 3 over 2, then you get the Gegenbauer polynomial. So Gegenbauer polys G sub ni are, sorry, let me say G sub n sub k are pk alpha alpha with alpha equals n minus 3 over 2. Okay, so those are special polynomials, and these have, so they have many special properties. They're orthogonal polynomials for suitable measures. They satisfy a second order recurrence relation. They satisfy a second order differential equation, and so on. There's a lot of interesting properties they have. I'm just going to state a few. So yeah, let's see. Sorry? Alpha equals n minus 3 over 2. N is the dimension of the space, right? So some properties. So one, pk alpha beta of 1. So I'm just going to write the properties for the whole Jacobi polynomials, and you can specialize to alpha and beta equals, alpha equals beta equals that to get the Gegenbauers. This is k plus alpha over k. I hope I wrote this right. Yeah. So you just plug in, see that I equals k is the only one which survives. 2. They satisfy this. They're orthogonal polynomials for the following measures. So pk alpha beta of t. Alpha and beta is not parenthesized. Sorry, there's no parentheses around alpha and beta. It doesn't matter. Pk alpha beta of t, pl alpha beta of t times 1 minus t to the alpha, 1 plus t to the beta, dt. So this is the measure. If you integrate with respect to that measure from -1 to 1, you get delta sub kl times, I can never, is this var pi or var omega, or do people remember? So the omega with a bar on top. I think it's, somebody told me it's var pi really, but anyway, it is what it is. Pk, yeah, pk alpha beta t and then pl alpha beta t. And then you get the Dirac of kl times omega bar of k alpha beta, okay? Yeah, when alpha equals beta, when in the Gegenbaner situation, you get 1 minus t squared to the alpha, or 1 minus t squared to the n minus 3 over 2, which is the projection of the surface measure. So they're orthogonal with respect to the surface measure on Sn minus 1. Yeah, I'm going to say what that is, where I'm glad you asked. With omega bar, here, you'll like this. Omega bar alpha beta equals the following fun formula, 2 to the alpha plus beta plus 1. I mean, the key part is not what the constant is, it's the fact that they're orthogonal. So the delta k, but anyway, but here it is, k plus alpha plus 1, gamma of k plus beta plus 1 over k factorial 2k plus alpha plus beta plus 1, gamma of k plus alpha plus beta plus 1. Okay, that's what omega bar is. Okay, some constant. Okay, then there's a very interesting summation formula. Well, I mean, if you take p sub alpha beta of t and p sub alpha beta of s for different t and s, and you sum it over I going from 1 to k, then you get a very nice formula. It's called the Christoffel Darboux. Formula. What does it say? It says p sub k plus 1 alpha beta of t, p sub k alpha beta of s minus p sub k alpha beta of t, p sub k plus 1 alpha beta of s. So this is equal to some constant. Let's just write that down. So 2k plus alpha plus beta plus 2, 2k plus alpha plus beta plus 1 over twice k plus 1, k plus alpha plus beta plus 1. Anyway, the constant is not particularly important. There is a constant. And then the sum I goes from 0 to k. Again, there's a constant, which is omega bar of k alpha beta over omega bar of L alpha beta. Sorry, I alpha beta. I is the index going from 0 to k, times p sub I alpha beta of t, p sub I alpha beta of s. Okay, so the point is, right, if you sum pi of t times pi of s, I going from 0 to k, you get basically like a determinant kind of thing, okay, between p sub k plus 1 and p sub k. All right, so that's the Christoffel Darboux formula. And corollary of this formula is if you take a limit as s goes to t, you can rewrite that. I mean, you can divide this by t minus s and take a limit, and so you get that p sub k plus 1 alpha beta of t, the derivative of this with respect to t, and p sub k of alpha beta of t minus p sub k alpha beta of t, p sub k plus 1. Sorry, read the other way around. Yeah, sorry, this p sub k plus 1 alpha beta of t, p sub k alpha beta of t prime, that's positive. Okay, this Wronskian determinant is positive. So that implies, So all this is leading up to something. Namely, these things are orthogonal polynomials. And this is sort of a general phenomenon for orthogonal polynomials that you have interlacing of roots. So all the roots of p sub k are in minus 1, 1. They're all real. And the roots of p sub k and p sub k plus 1 are interlaced between them. Okay? So between any two roots of p sub k, you're going to get a root of p sub k plus 1, and so on. Interlacing of roots. What does it say? All zeros are real and in interval from minus 1 to 1. And let t sub 1 of k alpha beta dot 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 t sub k of k alpha beta be all the roots of pk, which has degree k. So there's k roots, and they're all right. So I'm going to arrange them, in descending order. Okay, so t sub 1 is the largest, and t sub k is the smallest, and they're all between 1 and minus 1. Okay, so then the interlacing says the following thing. So then for k equals 1 dot 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 1 2 etc. and I equals 1 2 etc. we have that t sub I plus 1 k plus 1 alpha beta that this is less than ti k alpha beta. This is less than t sub I of k plus 1 alpha beta. It's less than 1. Okay, so the ith root of the k plus 1th polynomial is bigger than the ith root of the kth polynomial, but this root is between the next one. Okay, so the next smallest root. So the roots interlace. Okay. The roots are in minus 1 1. Yeah, I mean the polynomial is defined. So in particular, I think when n equals 2, you get the Chebyshev polynomial. So I mean the roots are really in minus 1 1. Wait, where the measure is from? Yeah, this integral is from minus 1 1. The measure is on all the inner product possibilities, right? Sorry? You can't see something? The corollary, yeah. Oh, okay. So it says if s goes to t, then you get the following thing. So you take the derivative of p sub k plus 1 of t times p sub k of t minus the p sub k plus 1 of t times the derivative. So this is the Wronskian, basically, between pk and, sorry? The variable everywhere is t, yeah, it's the same variable. I mean, if you divide this by t minus s and you sort of do a little bit of algebra, you can sort of get this. Ti plus 1 is less than ti, yeah. T1 is the biggest one, and then the remaining ones decrease, right? So ti plus 1, so the k plus 1 thing sandwiches the one from the lower polynomial. Okay. And then let me just write down the last property. So when this is for Gegenbauers, so when alpha equals beta equals n minus 3 over 2, p alpha beta of k of t times p. So if you multiply two of these polynomials, it's still a positive definite kernel. PL, then that's equal to some I goes from. So this is some polynomial of degree k plus L, and so therefore it's a non-negative linear combination AI KL of PI alpha beta of t for some suitable non-negative coefficients AI KL. Okay. So if you multiply two positive definite polynomials, you get a positive definite polynomial. Okay. All right. All right, so those are all the properties I want to list. Let me say, now go on to Delsarts' lemma. So Delsarts' theorem. So this is very, very easy to state and prove. So let alpha equals n minus 3 over 2, and let f of t be positive definite. So it's the sum I goes from 0 to k. Let's say it's degree k of f sub I. These are just non-negative coefficients times pi alpha alpha, the Gegenbauers of t. So this is some polynomial of degree k. And we're going to assume that the zeroth, by the way, the p sub 0 is the constant function 1, just like we had the. So it's a degree 0 polynomial. I mean, it's a degree 0 thing, and so it's constant, and therefore, right, it's 0 plus alpha choose 0, which is 1. Okay, so it's normalized to be 1. Yeah. Oh, that this doesn't depend on. Oh, yeah. I mean, I didn't explicitly write it. Yeah, but sure. Yeah, let me just say depending on. Yeah, on alpha or n. Yeah. Sorry? AIs. Yeah, I mean, all these polynomials have, yeah, I guess I didn't say all these things, but it's kind of evident from the definition that the polynomials have rational coefficients, and so if you expand in a basis, you're going to get rational coefficients. K is some degree. I mean, it's some arbitrary degree. So you take some arbitrary degree linear combination of these things, which is non-negative coefficients. So you're going to assume the first one is strictly positive, cannot be 0, and the other ones are non-negative. Fi greater than or equal to 0 for I going from 1 dot k, some k, and then suppose that. So suppose you found a function which satisfies f of t is less than or equal to 0 for minus 1 less than or equal to t less than or equal to cosine of theta. Right, where theta is given. So theta is going. So this is sort of going to give you an upper bound for the spherical chord problem. So theta is a minimal angle that's given to you. You want to find a bound on the size of spherical chords with that minimal angle. So then the theorem says then any chord, spherical chord of minimal angle, at least theta 0, at least theta has size bounded by f of 1 over f sub 0. Okay, that's the theorem. Okay. So this is called this is the linear programming bound for codes. Spherical codes. Why is it a linear programming bound? So if you think about it, these polynomials are given to you. They're fixed. So the variables in your linear program are these things. They have linear constraints greater than or equal to 0. f0 you can usually normalize to be 1. Okay, it's some positive number, but it's going to appear in the denominator anyway. So you set f0 equals 1. So that's a linear constraint. And then you have a whole bunch of, you have a continuum of linear constraints, f of t less than or equal to 0 for every t in here. But they're all linear constraints. Okay? And then finally, your objective function is f of 1, which is a linear function of your variables. So it's a linear program. I mean, admittedly with infinitely many constraints, but nevertheless, it's a linear program. So you can try to solve it. Usually, you approximate by taking a mesh in here rather than, and then doing a little bit of approximation. But anyhow, that's why it's called the linear programming bound. And you see that it has nothing to do with any putative codes. Like if you find a function, this gives you an upper bound. Okay, all it takes as input is the angle theta, and sort of if your function is set up so that it satisfies these constraints, it gives you an upper bound on the size of any code. And sometimes that upper bound matches the size of a code that you can actually manufacture with that minimal angle. And then you say that the bound is sharp. And whenever you get a sharp bound, you can prove lots more stuff. Like usually you can prove the code is unique and optimal and so on. Okay, but let's see the proof. The proof is a couple of lines. It's very straightforward. Okay, so C f of 1. So C is any spherical code satisfying these properties is greater than or equal to sum of x and y in C of f of x, y. So why is this true? So this is just computing the diagonal. So whenever x equals y, you get the inner product is 1, so you get f of 1, and that happens for every x in C, so you get C times that. And whenever x is different from y, the inner product is less than or equal to cosine theta, and so f is non-positive there, and so you get this inequality. Okay, so this is just counting the diagonal. Okay, and then you can rewrite this as, since f is the linear combination, so this is sum over I goes from 0 to k of fi of x. I've switched the summation, right? So this would be a sum over x and y and c of fi times pi, but I'm just switching the summation. Okay, so pi alpha alpha of xy. Okay, so this is fine. And the point is that I'm going to claim that this is at least f0 c squared. Okay, so if you look at the I equals 0 term, you get f0, and p0 is 1. So you're just counting 1 for all pairs of points in C, so you get c squared, size of c squared. For all the other things, this sum, because you have a positive definite kernel, is non-negative. And fi is non-negative, so whatever you have, you get this inequality. Okay, so that tells you that C, and then you just divide. C is less than or equal to 1. That's it. Okay, so it's very. Yeah, I mean, right. You get what? Yeah, I mean, you could potentially take, right, an infinite linear combination and try to work with that. Right, I mean, usually people, what they do is they want a finite dimensional program. So what they do is they want finitely many coefficients, and they also have to sort of replace this by a mesh so that you get finitely many linear constraints. And that's how usually in practice you would try to solve this. Then what happens is you find an f which only satisfies the inequality at those points, but then if f sort of, if f dips above 0 at certain points, you can just translate it down, and that gives you a little loss in the linear objective function, but that's, you still get a bound. So that's in practice what people do, and sometimes it happens that you don't have to shift f. That approximation is good enough. Yeah, but typically you want a polynomial space just because it's finite dimensional. Okay. Any questions? Where are we? 35. Right. So, yeah. So let me do a couple of things. So I'll rearrange the sequence a little bit. So what I'm going to do is I'm going to give you the sharp examples for kissing numbers in 8 and 24 dimensions. Then I'm going to tell you, and then I will do the asymptotics by Kabacanski and Levenstein, and then I will leave the linear programming bounds for sphere packings for later, and we'll probably do that on Monday afternoon. Okay, so once you have these bounds for codes, let's see some very interesting examples. So sharp bounds. So I guess I still owe you the Kabacanski-Lenventein part of that subsection, which we'll get to. So examples. So there are many examples of spherical codes with sharp upper bounds, but I'm just going to give you two of them. So one, kissing number in 8 dimensions. So right, you have the E8 root lattice, and it has 240 minimal vectors, and they have norm 2. So let's normalize them. So they have norm 1, and then the inner products are 0 or plus minus a half, or plus minus 1. Okay? So those are the possible inner products. So plus minus 1 happens when you're either the same point or the antipode, and in all other cases you're either orthogonal or you have inner product plus or minus a half, right? I mean, this is like Tathagata's lecture. You see, you would have inner product 0 or plus minus 1, but we've normalized them, so you just divide by 2. Okay, so those are the possible inner products. And what happens is, in order to get a sharp bound, it must be true that whenever we had an inequality, you have an equality when you actually plug in the code that matches the bound. So in particular, what the things that must happen is that f has to, so whenever x and y, x dot y is less than is not 1, then f had better vanish at those points, right? Because if you know that f is non-positive, if f was actually negative, you would have a slackness in this inequality, and that's not allowed because you want a sharp bound. We're assuming there's a sharp bound. So, I mean, that's what's going to happen, but I'm just sort of motivating what the function is going to be. Okay, so f has to vanish at those points, all those inner products, which are not 1. And the other thing that it tells you is that that code has to, the Gegenbaner polynomial has to vanish when you sum over. And that actually is a property of the code. It becomes a design. So we won't get into that too much, but this part is quite important. And so the function just turns out to be the following. So f of x equals x plus 1, x plus a half squared, x squared, x minus a half. Okay, so if you look at this function, it's going to change sign at 1/2, which is the right. So this function is going to be positive beyond 1/2, and is going to be negative, but it's going to have a single 0 at 1/2. It's going to dip down below 0. It's going to have a double 0 at 0 and minus a half, and a single 0 at minus 1. Okay, that's what the function looks like. All right, it has to stay below 0 as long as you're less than a half. Okay. Anyway, that's one function that does the job, and this function you can check. So this function is positive definite. I mean, you can compute the Gegenbaner polynomials completely explicitly in the, for n equals 8, and the bound you get gives a bound of 240 exactly. I mean, it's exactly on the nose 240. So that matches the 240 lower bound that you get. So the kissing configuration of E8 is optimal, and also you can show by using these facts, by using the fact that you had equality everywhere, that it's unique. It's the unique one that gives you 240 points. Okay, and then let me just tell you what the one is for the Leech lattice. Its kissing configuration has 196560 vectors. So again, the normalized inner products. So the least vectors have norm 4, so you're going to get denominators of 4 in the normalized inner products between the 196,560 minimal vectors are 0, plus minus a quarter, plus minus a half, plus minus 1. Okay, so the function is x plus 1, x plus a half squared, x plus a quarter squared, x squared, x minus a squared, x minus a half. Yeah, so this is a function. I mean, I'm just plugging into the Delsarts theorem. So it says, yeah, this is for any spherical code, right? For a collection of points on the sphere, right? That you get it says that any spherical code of minimal angle at least this much. Oh yeah, so theta, I should say, here theta is pi over 3, so that cosine theta is 1/2. So that's the maximal. That's where you need to change sign. So it's saying minimal. So any code of minimal angle, at least theta can have at most this many points. So when you use this function for the 8-dimensional linear programming bound for theta equals pi over 3, you get an upper bound. That bound f of 1 over f0 is 240. But you already know you can get 240 points as a lower bound from the E8 kissing configuration. So the upper bound and lower bound match each other. So there's no other, that's the answer. And then you can show that it's unique also by using some of these inequalities, the fact that they are sharp. Okay, and then for the Leech lattice, this is the corresponding thing, and it gives. So you can check this is positive, definite, and gives upper bound of exactly 196,560. So get optimality and uniqueness. So those are two interesting examples. You can do this for other spherical codes of different other spherical, other minimal angles. There are many instances in which you get a sharp bound. I won't write down all of them, but they're enumerated in a lot of these instances where you get a sharp bound were computed by Levenstein once upon a time, and you can see them in this paper also. So Henry and I wrote a paper on universal optimality in the spherical code case. So, universally optimal distributions of points on spheres. And at the beginning of that paper, there's a table which lists all the examples where you get a sharp bound in just the spherical code case. There are many other cases in projective space and so on, and all sorts of interesting situations where you get a sharp bound. But it's not something that's happens all the time. I mean, it's a very exceptional occurrence. Just while we're here, let me just say what happens if you try to optimize and find. I mean, typically you don't know what these functions are going to look like. In 8 and 24 dimensions, it just happens that these functions give you a sharp bound. Typically what you would do is, if you're trying to get an upper bound for kissing number in say 3 dimensions, you would just run the linear program and see what bound you get. And if you do that, you get a bound of 13 point something in 3 dimensions, which is what I was alluding to. So you have a lower bound of 12, you have upper bound of 13, and you still have to do some work to solve. And in 4 dimensions, you get a bound of 25 point something. So it's either 24 or 25. Okay. So I have about 10 minutes left. So I'm going to give you, I'm going to tell you a little bit about the. In 4 dimensions, it's 24. Yeah, now we know it, right? Right. Okay, so let me get back to Kabacanski Lenventein. So okay. So back to Lenventein. So we're going to talk about the asymptotic of spherical codes. So lemma 3 for theta in between 0 and pi over 2 and n going to infinity. So I'm just going to sketch the proof of this lemma. I'm not going to do all the details. It takes a little bit to fill in all the details. Then the assertion is that the size of a spherical code, so on Sn minus 1 of minimal angle at least theta satisfies. So you fix the theta and then you let the dimension go to infinity, then it says that any spherical code of minimal angle at least theta satisfies C is less than or equal to the size of C is at most this function. So it's called m of n theta. This is some function which has the following definition, where I'm going to say that it's defined by log m and theta over n is less than or equal to 1 plus sine theta over 2 sine theta log of 1 plus sine theta over 2 sine theta minus 1 minus sine theta over 2 sine theta log of 1 minus sine theta over 2 sine theta. Okay, something fairly complicated, but anyway, this defines m and theta as a function of n and theta, and it's saying that you get, so basically this tells you the exponent of the size of the size of the spherical code. It's telling you the asymptotic exponent, okay, or at least some bound for it. So the proof, let me just say what the proof idea is that you use the positive, you plug it into Delsart, use the positive definite function, and we have to show that it's positive definite, but it turns out you can do it by using Christoffel Darboux. F of t is p sub k plus 1 alpha alpha of t p sub k alpha alpha of s. I'm going to tell you what s is, minus p sub k alpha alpha of t p sub k plus 1 alpha alpha of s squared divided by t minus s, where s equals cosine theta. So to get an upper bound, and k and k plus 1 are chosen, k and k plus 1 chosen so that t1 of k alpha alpha, s is sandwiched between t1 of k alpha alpha and t1 of k plus 1 alpha alpha. I mean, actually in the end you have to do a little bit more work, but I'm sort of going to wave my hands and not talk about all the details. This function, it turns out, is positive definite. You can show it by using Christoffel Darboux, and you can compute its f of 1 and f0 also by using these formulas that I've listed, those properties that I listed. And you get a bound, and that bound has, turns out to have these properties. Okay, it's a few pages of work, but it's If you really want to see all the details, you can look in Zong. Okay. Yeah, and then you get some formula which depends on the T1s, and then you have to sort of follow it up by using the asymptotics of the T1s, which you can get a handle on, and then using Stirling's formula. So you have to do a little bit of work, but this sort of thing it might be reminiscent of Stirling's formula, but for binomial coefficients or something. Sorry? Yeah, exactly, right. But I mean, if you do Stirling's formula for m choose n, right? I mean, you get n to the n, e to the minus n. So you get things like n to the n, m to the m, and so on. So that, yeah, it's kind of, you get that entropy kind of function showing up. Yeah. Okay. So the corollary is that the kissing number in n dimensions is bounded by here's the asymptotic exponent, 0.401 n 1 plus small o of 1. And to see this, you just use theta equals pi over 3. Okay. In this, you plug it in and you get the right exponent. So, oh, here, 0.401 times n. Times 1 plus small o of 1. Yeah, sorry. Okay, and then here's the jump from here's lemma 4, which tells you how to go to sphere packings, which is quite a nice lemma. So for a certain small theta, the sphere packing density in n dimensions is bounded above by sine theta over 2 to the n times m of n plus 1 theta. Okay, so let's see where this comes from. So it's saying if you get a nice bound on spherical codes, then you can make that into a nice bound on the density of sphere packings. So why is that? So proof is let R be some positive number, real number, let's say it could be large, and H hyperplane through the center of the ball R S n plus 1. Okay. So you take a ball in n plus 1 dimensions, and you take a hyperplane through that. Okay. And in H, we can construct, so H is n dimensional, okay, and you can construct sphere packing, an n dimensional sphere packing of unit spheres with density delta of Sn or Bn, okay, with the maximum possible density, right? So suppose you have a maximally dense packing in n dimensions. That's what you look on that hyperplane. All right, so then, right, by shifting the packing slightly, you can assume that you have at least n plus 1, there are at least r to the m times delta times the density. So this is the volume of H intersect sort of r times Sn plus 1, so that this sphere centers lie in H intersect R Bm plus 1. Okay? I mean, that's the volume of this thing, and R to the m is the volume, and that times the density is the number of sphere centers that should be there, right? So then what you do is you project these to the upper hemisphere. So I mean, roughly the picture is like this. So you have this, I mean, here is this hyperplane, H, and here's this sort of R, Bm plus 1, and you get a bunch of sphere centers over here on this hyperplane. And what you do is, for each of them, you project them up. Okay, so whatever is inside this ball, you project it just to the upper hemisphere. Okay, so within this hyperplane, they had distance at least 2 because it's a sphere packing. And so if you project up, the distance cannot decrease, it only can increase. So they still have distance at least 2 when you look at the resultant spherical code that you get on the sphere. You project all of them, you get some spherical code. Okay, so project these perpendicularly to H up to the upper hemisphere. The Euclidean distance between points is at least 2. Okay, and so that means the angular distance. So we have 2 points with distance at least 2. Then whatever the angular distance is, that's going to satisfy the following property. So the angular distance is at least theta, where sine theta over 2 is 1 over r. So in other words, the radius of this ball is r. So it's just saying twice r sine theta over 2, which is the distance is at least 2. Okay, it's just rewriting that, saying that the angular distance must be at least sine inverse of 1 over r times 2. Okay, so that tells you that r to the n delta of bn is less than or equal to m of n plus 1 theta for that theta. Okay, so that tells you that delta of bn is at least sine theta 1 over r to the n, but 1 over r is sine theta over 2, so sine theta over 2 to the n times m of n plus 1 theta. So that proves that lemma. Okay, so once you get a bound on spherical codes, you can get a bound on sphere packings. And then let me just finish and write the sphere packing bound that you get from this. So then theorem Kabacanski-Lenventein that delta of Bn is less than or equal to 2 to the minus 0.599 n times 1 plus small o of 1. Okay, so you get that exponent minus 0.599. Here's a proof. So this is the best asymptotic exponent that we have till now. Okay, so it would be nice to improve it. So I'll talk about Kohnelke's bounds for sphere packing next time, and potentially they could be used to improve this. These bounds can be recovered. I mean, you can at least match these bounds using the Kohnelke's bounds, but you can improve them by a constant factor, but not by the exponent, but not the exponent so far. But if anybody has ideas, that would be fantastic to improve the exponent using the Corollary bounds. Okay, so proof, we check the following thing. This is an easy numerical exercise, 1 plus sine theta, 2 sine theta, log of 1 plus sine theta. So that function that I wrote down, minus 1 minus sine theta over 2 sine theta, log of that. That's less than equal to minus 1/2 log of 1 minus cosine theta minus 0.599 log 2. Okay, so this is, so you can just make your function equal to this plus this term, and then just see that that has a that are actually bounded by this constant number. I mean, that's a little bit of an easy calculus exercise, but and the equality is attained at some theta 0. So for 0 less than theta 0, which is approximately 63 degrees. That's where the minimum is actually attained for that function plus this thing. So that tells you that mn theta. So you can write. So then that tells you mn theta is less than equal to 1 minus cosine theta to the minus 0.5 n 2 to the minus 0.0. Oh, I should say, sorry, this is not 599. This is 0.099. Sorry, 0.99 n. Right, so the e to the minus this becomes 2 to the minus 0.99 n, and this is 2 sine squared theta over 2. So this becomes 2 to the minus 0.599 n when you combine with this, and then sine theta over 2 to the minus n. And then when you multiply by that guy, the sine theta over 2 to the n, so that tells you that delta of Pn less than equal to minus 0.599. And there's some factors that I've waved my hands. That's why you get the 1 plus. Asymptotic is this thing. Okay, I think this is a good place to stop. This bound is for all n. Yeah. Not that I know of. Yeah, that's a good question. I mean, nobody has really, studied, what happens if you have extra structure on an dimensional space. But it's possible that you could get better bounds for certain sequences. But most of the bounds upper bounds that have been written down have been fairly uniform in n.
And if we fix n, then can we do better, like in terms of computing this theta? Like can we say more? So this is for all n.
Yeah.
There is some lower bound for theta.
Yeah. So I mean, right. It turns out that if you concentrate on a particular n, it's better to do the bounds for the Corollary bounds for sphere packing, which are meant for for that situation. So in that situation, you have different positive definite kernels essentially. So I'll describe it, in the second lecture on Monday. But there's a separate linear programming bound, and those are set up for sphere packing, and they give you in general better bounds for low dimensions. Yeah, and supposed to give better bounds for asymptotically too, but we don't know that yet. Yeah. Yeah. So I'm right. I mean, I sort of waved my hands, but the way it works out is this is chosen for. No, the function itself is defined for all t. Yeah, you can show that works out. Yeah, so s is, I mean, t minus s, that gives you the, so this thing is non. Yeah. But divided, oh yeah, sorry, this is divided by t minus. That's why you get the sign change. But in fact, it's not, it doesn't blow up at t equals s because, the numerator also vanishes. Yeah. Okay, all right.